This is a lesson on finding derivatives of polynomials and exponential functions. Our focus in this lesson will be discovering the power rule and finding derivatives. So remember in our last unit we talked about the limit definition for finding a derivative. The limit as h approaches 0 of f of x plus h minus f of x all over h. So for example, let's say I had my function of, let's just say it's simply a constant, so 2. If I were to apply that limit definition to this function, well, it would be the limit as h approaches 0. There's really no place to sub in this x plus h. So really it would just be 2 minus my function, which is 2, all over h. When you simplify, we get, well, limit as h approaches 0 of 0 over h, which is in fact 0. And it makes sense because if we were to graph this line, it'd be a horizontal line right at positive 2. And we know that derivatives really represent slope at any given point. So the slope of a horizontal line is 0 here. So we actually first come up with our first rule in differentiation, which is the derivative of any constant, c we'll call it, is always 0. Let's take a look at another example. It says, given that our function is now x, find its derivative. So let's use our long limit definition from before. So limit as h approaches 0, f of x plus h minus f of x all over h. Now if we sub in x plus h wherever I see an x, it would be the limit as h approaches 0, x plus h minus f of x, which is actually x in this case, all over h. When we simplify, we get the limit as h approaches 0. Notice that on top, the x's actually will cancel. And what I'm left with is simply h over h, which reduces to 1. So this is another rule in actually differentiation that really the derivative of x is 1. So we already know our derivative of x is 1. Let's take a look at another case. For example, find the derivative of f of x equals x cubed. So we know our limit definition from before, limit as h approaches 0 of f of x plus h minus f of x all over h. If we apply that to x cubed here, subbing in x plus h, I get limit as h approaches 0. It'd be x plus h to the third minus f of x, which is x cubed, all over h. Now I could spend some time really multiplying this out, but if you know the binomial theorem here, we can simplify that to the limit as h approaches 0. It becomes x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. Notice that our original function x cubed cancels out of here. And if we cancel one of the h's from the top, we can simplify this to be the limit as h approaches 0. Looks like we're left with 3x squared plus 3xh plus h squared. And by substitution, if we sub in 0, our answer becomes 3x squared. So what I want you to notice is our result here, 3x squared, compared to our original function, x cubed. Some of you might recognize that here our power is 3. And notice how the coefficient in our answer is 3, but it's to the 1 less power for above, so it would be 3x squared instead of x cubed. Well, this is known as the power rule. So in general, the power rule is if any n is any real number, we can actually express the power rule as nx to the n minus 1. So for example, if I have a function, let's say x to the 4th this time. What the power rule says I can do is I can really just bring that power in front. So it becomes 4x, and it's always to the 1 less power from before. So it would be to the 4 minus 1 power, which actually simplifies to 4x cubed. There's my answer. And we can actually do this with any function. So for example, we can use it here in our two examples of f of x equals 1 over x squared and we can use it with radical and rational powers as well. What we know is that we can simplify this 1 over x to the second to be x to the negative 2 power. And let's apply the power rule here. So, knowing that our exponent now becomes the coefficient in front, it would become negative 2x, and remember it's 1 less power, so it would be negative 2 minus 1 power, which becomes negative 2x to the negative 3. Now normally we don't write it with negative exponents, so we might want to simplify this to be negative 2 all over x to the third, quicker than our limit definition. In the next example, we can actually rewrite this radical as a rational exponent. So let's rewrite this function as y equals x to the 2/3 power. And we can actually apply it here as well. So notice our power here is 2/3. If we bring that in front, it becomes 2/3 x to the, remember it's always 1 less that power, so 2/3 minus 1 power, which let's think of that 1 as maybe 3/3. Might be a little bit helpful here. So if I simplify, I get 2/3 x to the, well, 2/3 minus 3/3 becomes negative 1/3. And again, we might not write it this way. So in its simplest form, we'd write it as 2 over 3x to the 1/3, which we can represent as the cube root of x. There's my final answer there. So we can apply it to both rationals, and we can also apply it to radicals or rational exponents as well. Another rule with differentiation is this constant multiple rule. Really what it says is if we have any kind of coefficient in front of the function, we can kind of factor that out and leave that for last by multiplying it to our end result. So for example, we can use it in these cases where my function, let's say, is 3x to the 5th power. Well, by the power rule itself, that 5 will be brought down in front, and what happens is we actually multiply it to that coefficient of 3. So it becomes 15 x to the, again, still 1 less power, so 5 minus 1 power, which would become 15 x to the 4th. So any kind of coefficient, we would multiply that power within the power rule there. And so even with like limit laws, we can also do the sum and difference rule as well with differentiation. So if we have this big long polynomial here in example 5, we can actually just apply the power rule to each separate case. So the derivative of x to the 8th, well, bringing that in front, and 1 less power would become 8x to the 7th. Notice how we have a coefficient in the next one, 12. Well, the power rule, if I bring that down in front, I'd multiply it by that 12. So it become positive 60x to the 1 less power would be 4. And again, with the negative 4 in front, I'd bring that power rule, come in front, and becomes negative 16x to the 3rd, 1 less power. And then the 10x cubed, well, by power rule, bringing that down in front, would be 30x to the 2nd. And notice how we don't have a power, but let's treat it as a power of 1 for this one. Well, that's just going to simply be negative x as our derivative, because it would be x to the 0, which is just 1. And remember from before that the derivative of any constant is 0. So this would be our end result, the derivative of that function. Now let's take a look at how we can actually apply derivatives to simplify some things. So remember in our last unit we talked about finding the slope of the tangent line, and again we used that long definition to find the slope of f of x plus h minus f of x all over h. But we know the power rule here. And what we know about tangent lines that are specifically horizontal, well, we know their slopes are 0. So what does that mean for us? It means when the derivative is 0. So let's find all the points on the curve where the tangent line is horizontal. Well, that's really finding the derivative and setting it equal to 0. So notice how our polynomial up above has a combination of x to the 4th minus 6x squared plus 4. So let's take these in separate cases. The derivative of x to the 4th by the power rule would become 4x to the 3rd. The derivative of negative 6x squared would become minus 12x. And of course the derivative of a constant is 0. So this is our derivative of y. What do we want to do with that? Well, we want to find all values when it's horizontal. So when that slope is 0, and let's solve for x. If you notice, we have a common factor here. In fact, we can actually factor out a 4x out of each of those terms. And what I'm left with is x squared minus 3. Now, by the zero product rule, we can actually say, well, that means that either 4x equals 0 or x squared minus 3 equals 0. Well, solving the first equation, that just simply means when x is 0 is one point where the tangent line is horizontal. And if we solve our other one by adding 3 and taking the square root here, remember we have plus or minus, so that means that also square root of 3 and the other last spot would be negative square root 3 is when our tangent line is horizontal as well along this curve. Now we can also apply derivatives to physics applications such as velocity and acceleration. Here we have an equation of a particle moving along some kind of line, and here's its position function of 2t cubed minus 5t squared plus 3t plus 4, where s is measured in centimeters and t is in seconds. So it says find the acceleration of the function, okay, as a function of time, and also what is the acceleration after 2 seconds. So what we know from before is that the derivative of position is our velocity function. And we know that the derivative of velocity is our acceleration function. So here we actually have to find the second derivative of this position. So our first derivative, f prime of t, well, by the power rule, notice how our 2t cubed, well, that derivative of 2t cubed would become 6t squared, one less power. And the derivative of our negative 5t squared would become minus 10t. And then the derivative of 3t just becomes simply plus 3. This is our velocity function. And we know that the derivative of our velocity is going to be our acceleration. So let's find the derivative of this. Well, the derivative of 6t squared would now become 12t, and the derivative of negative 10t would now become minus 10, and of course the derivative of 3 is 0. So here's my acceleration function in terms of time, and what I want to know is what the acceleration is after 2 seconds. Well, all we need to do is really simply sub in 2 for our t, and if we sub in 2, we get an answer of 14, which our units, remember, in this case would be centimeters per second squared. So this is the acceleration after 2 seconds. The last rule is the derivative of natural exponential function, e to the x. In fact, it's itself e to the x. And we actually discovered this when we did our group work a long time ago. We saw the graph of e to the x in one of those examples, and I think it was group work 2.8. And sketching the derivative here, well, we know that the slope was less steep, and in fact, when we sketched the derivative, it looked exactly like its original function. So it makes sense graphically, and yeah, the derivative of e to the x is e to the x. So for example, if my function, let's say, was 3e to the x minus 4x to the fifth, we can actually apply this rule to finding the derivative of 3 to the x. Now notice that the 3 is a coefficient, so we can actually bring that out of our derivative, and we know that the derivative of e to the x is e to the x, so what's interesting about this example is that our derivative will be 3e to the x from that first function, first term, and by the power rule in the second term, bringing that 5 down in front, it becomes negative 20x to the 1 less power will be to the fourth. So here's our derivative of that function. So there's a lot of rules in this lesson. Just make sure you've written them down and written down some of those key examples, and follow through with the discussion page on Canvas. Hope you have a great night.